Hi. Hello. I want to keep talking about this stuff on infinite series. So we're still in section 10.2, and I think we will be for a couple more of these infinite series. And I want to keep talking about that series that we had talked about last time, which is where a sub n, the sequence was basically this. It was 1/2 raised to the n minus 1 power, or 1 over 2 to the n minus 1. That was the sequence that we had looked at, and the series that we had looked at was the sum of those. So big S sub n is the sum from little n equals 1 to big N of 1 over 2 to the n minus 1. And what we found from that was that we could write that like this. Since the first term is 1, if we plug in n equals 1 here, we get 1 over 2 to the 0 power. So in this case, this was 1 plus r plus r squared plus r cubed plus dot 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 all the way to r to the big N minus 1 power. And we looked at S sub 5 as the fifth partial sum. Fifth partial sum. And we calculated it, and what I did it sort of by a trick, but basically what we showed was that S sub 5 was 1 minus 1/2 raised to the 4th all over 1 minus 1/2. All right, so what we want to do here is now actually do infinite series. We want to look at S sub infinity. So now let's do the infinite sum. Okay, so S sub infinity is a way to write it, I suppose, and it is going to be, I'm going to write it like this. So this is the sum of n equals 1 to infinity of 1 over 2 to the n minus 1. And I think the way we can approach that is well, it's going to be the same as it is above, but we're going to go out to infinity. So this is the limit as big N goes to infinity of the sum from little n equals 1 to big N of 1 over 2 to the n minus 1. And that we're going to start with that on the next page, but that's the we're going to apply the same sort of technique that we did in the fifth partial sum to this one. So if you remember, that technique was as follows. What we did was we have, I'm going to keep writing it as S sub infinity, and I don't like that notation, but there it is. It is 1 plus r plus r squared plus r cubed plus r to the 4th plus dot dot dot, and I'm just going to leave it as plus dot 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 because we're going to go on forever. So infinite number of terms. Okay, and if you remember, what I did was I took the left-hand side and the right-hand side and subtracted from it r multiplied by that infinite sum. And that was 1 plus r squared plus r cubed plus r to the fourth plus dot dot dot, and all of that minus r plus r squared plus r cubed plus r to the fourth plus r to the fifth plus dot dot dot. And I know that it's funky notation, but you know, you can visualize it, right? And it's the same thing we did last time, and just like last time, all the terms cancel out except for the very first term and the very last term. The very first term on the left-hand side stays, but everything else cancels out. Everything cancels out, not on the left-hand side, but in that one, everything cancels out except for the first thing. In this one, only the last thing remains. Okay? Whatever it is. Okay? So, boom. So, again, I factor out. So, s sub infinity multiplied by 1 minus r equals 1 minus, really, I mean, this is sort of like an r sub infinity, and that's probably not the best way to write it. So what I'll do is write it and then stop writing that line, and then just say that that's equal to the limit as, and I'm just going to call it something else, k goes to infinity of 1 minus r to the k. And you could do n to the infinity, r to the n minus 1, but I didn't do that. So this means that the partial sum, if I divide now, s sub infinity is given by the limit as k goes to infinity of 1 minus r to the k over 1 minus r. Okay, and this comes from, you know, you maybe even remember it from algebra 2 or geometry, algebra 2, s sub n equals 1 minus r to the n minus 1 all over 1 minus r. That probably is something I have my algebra students not memorize, but to use all the time. All right, so this will give you the nth partial sum. All we're doing now is taking that n to infinity. All right, well, if we use r equals a half, then s sub infinity equals the limit as k goes to infinity of 1 minus 1/2 to the k all over 1 minus a half. And what as k goes to infinity, what happens to 1/2 times itself over and over and over and over? I keep getting like 1/2 times 1/2 is a fourth, times 1/2 is an eighth, times 1/2 is a 16th. I get 0 essentially. So this will go to 0, and I get that the infinite sum is equal to 1 over 1 minus a half. which is 2. Okay, and that makes sense. If we keep adding up halves, a half plus a fourth plus an eighth plus a 16th, all that with 1 being the first term, we're going to get that it doesn't get past 2. All right? Well, let's take that a little more generally now, because if we write down there are two things to remember, that S sub infinity is the limit as k goes to infinity of 1 minus r to the k all over 1 minus r. Well, when will that converge? All right, that will converge if the numerator goes to 1. That is to say, if r to the r is a number that gets smaller and smaller and smaller if I keep multiplying it by itself. Okay, and that's going to happen not if r is less than 1, because r could be -5 or something like that. So it's if -1/2 or -1, if -1 is less than r is less than 1, then S sub infinity is 1 over 1 minus r. And that's really what I want to talk about, is that case. It's going to blow up otherwise. All right? If it's equal to 1, r, or if the ratio is larger than 1, even if it's a negative, it's still going to be something that it doesn't converge. But think about what we have here. We have S sub infinity can be written like this: 1 plus r squared plus r cubed plus r to the 4th plus ... So that's an infinite polynomial, and that's going to be equal to 1 over 1 minus r. Okay, and that's if the absolute value of r is less than 1. Okay. Well, if I just replace the r's with x's, r is just a name, right? So now I'm going to say 1 plus x squared plus x cubed plus x to the 4th plus ... And that is the same as 1 over 1 minus x. And that is true if the absolute value of x is less than 1. Think about the implications of that. On the left-hand side, I have a polynomial. Granted, it's a polynomial of infinite degree. But on the right-hand side, I have a rational function. With like an asymptote. Okay. So I have a rational function and I'm expressing it as a polynomial. And I think the implications of that are pretty significant. And what we're actually going to do later on, we'll spend some more time on this, is we're going to show that and find that any function, irrational, rational, or transcendental, can be expressed as a polynomial. All right, so we can apply a polynomial expression to something like e to the x, or sine of x, or inverse tangent of x. Things like that are going to have a polynomial expansion that is a function that, if I take it to an infinite number of terms, an infinite degree, it's going to be that otherwise transcendental or irrational kind of function. All right, so that was sort of the key for today, for this little segment, was that I can write a rational function as an infinite degree polynomial, okay, with certain conditions. With certain conditions like that. Okay? Thank you very much.